So before going into trees, so last time I mentioned the queue data structure can be implemented with both arrays and linked list. And I only explained how to do it with arrays, right? So if you remember, uh, this one. So as you can see here, queue I mentioned that it can be implemented with linked list as well, and I explain how to do it, and I ask you to do it if possible. So let's let's see how we can do it. Let's do a hands-on session and see how we can actually implement a queue using linked list. I think I explained how to do it. So basically the enqueue operation, the enqueue or the insert operation in the queue happens from the tail, right? So this is the tail side, this is the head side of a linked list. So this is the linked list and this is the head, this is the tail. So insert operation, when you insert a node, it will join the queue from this side. So this is the new node, so it will join to the end. Whereas DQ is about taking out the top node, like the first node in the linked list. So that will happen from this side. So we'll take out this node and we'll shift the head towards the next node, right? So that's the operation. Let me do a hands-on session. So let me share screen one. Okay. If you have also Visual Studio, please open it. So this is the implementation using array. So what we are going to do today is let me first copy. Okay, what I'm going to do is I'm going to just copy the link. I'm going to do it with single linked list. So you can do it with double linked list as well. So let's do it with single linked list. So what I'm going to do is I'm going to copy this code, single linked list, and I'm going to paste it over here. Yeah. So I'm going to change the name. Let's say queue underscore linked list. Okay. So what we have over here now is a linked list, right? So this is the implementation of a linked list. Okay. You can see the Visual Studio screen, right? Can you?
Yes, sir.
Okay. So this is the implementation of a linked list. So let's see how we can implement the enqueue and dequeue operations using this linked list. Okay. So I'm not going to use these functions that we have, like insert first, insert last. I'm not going to use them. I'm just going to write those two functions from the scratch. And let's start with dequeue. Okay. No, let's start with enqueue, the insert operation. So the signature would be something like this, void enqueue, and we need to insert a value, right? So the first thing we need to do, we need to see whether the list is empty, right? So how do we do that? We can simply check it using the head. So if the head is null, that means there's a empty list. So so if it is empty, so whatever the node that we have, we'll have to insert it. Okay. Before that, we need to create a node. Temp, new node, allow. Yeah, so we have a temporary node now, right? Temporary node. So if the linked list is empty, so we'll just simply equal both head and tail to that node that we created, right? And increase the size by 1. So if you are not familiar with what I'm doing, so basically what I'm doing is I'm using a linked list operation, the linked list data structure to implement a queue. So we are basically changing linked list into a queue, right? So yeah, so this is the first thing. And the second, so if the list is not empty, that means, let me annotate as well. So we have a list like this. So we have a list like this. Over here is the head, right? Over here is the tail, right? So we have now temp node, right? So this is the temp node, right? That we created. This is pointed to null. So now enqueue operation is the insert operation. In a queue, the insert operation happens from the tail, right? I mean from the end. So we join the queue from the end. So so how do you insert the node from the tail? Can someone tell me the uh, steps involved in adding a node from the tail? Anyone? What's the first thing we need to do? Dharma Ratna 3568. Can you hear me? Dharma Ratna.
Tail.nets.
Yeah, tail.next is what?
Equal null.
No, so tail dot, so this is the tail, right? Tail.next is this link. At the moment is connected to a null pointer. Now we need to connect it to this one, right? The temp, right? We need to make say tail.next is equal to temp, right? So that's how we make this connection. Tail.next, that means this link is equal to temp or connected to temp, right? Yeah, that's the first thing. And the second thing is we need to shift the tail pointer over to this node. Clear? Is that clear? Okay, I got the correct answer through the chat. Let me do it. Okay. So tail dot next equal to temp. That's the first thing. That here what we did is we make this connection. Then the next one we shift the tail to the temp, right? We shift it to temp, right? And size increased by 1. Is this clear? Okay. So instead of doing this, so this is what, I mean, basically what we did here was we implemented this function from the scratch, right? We didn't use any of these functions. Now, instead of doing all these, there's just one function that you can call, right? So you can just comment all this and you can implement this function using one of these methods. What can someone tell me what it is? What method you need to call in order to implement this function? Gunatilaka 3592.
Insert last.
Yeah, correct. So you can just call this function insert last. So it does the same job, right? Insert last function in a linked list. What it does is it insert a node from the end, right? So you can simply call this function as well. We can implement it using from the scratch like this. So both are possible. Okay. Um, now the next thing, let's just go with this one. Next function is dequeue, right? Dequeue is about taking the top node out, the first node in the queue out. Right? So we need to return something, return the value of that. Okay. Clear the row. I'll just keep it. Okay. What's the first thing we need to do? Anyone? These two things, like when you insert a node, there's one thing you need to do, which is to see whether the list is empty, right? Yeah, and when you take out a node, also you need to see whether the queue is empty, right? So how do you do that? Seems the same thing. So if the head is null, that means the queue is, there's no node, there are no nodes in the queue, right? You can simply say queue is empty. Okay, and you need to return something, because now the return type is here is integer, right? So you need to return something. So I mentioned last time, you can basically return the minimum integer number using this code. So for that, you need to have this. Isn't there? I need to import the limits. Seems not no longer needed. I thought you need to import this, include this library called limits. Okay. Anyway, let's go. But now, if the queue is empty, we can't return any node. We can't take out any node. So if it is not empty, so we need to take out the first node, which is this one, right? So we need to take out the first node, right? So we need this guy. So can someone tell me how to do it? How do you take out this guy? So when you take away this node, you need to return the value of that node as well. So it's not just about deleting this node. So if you read, the return type is integer. So the dequeue operation is about returning, while you delete the node, the top node, the node in at the beginning of the queue, you need to return its value as well, right? So there's two operations. You take out the value and delete the node, right? So anyone, how do you do that? So delete operation, I'm sure you should be familiar with it, right? So delete, how you do that? You basically create a temp pointer and link it to this guy, right? And then shift the head from here to here, right? And then delete temp, right? Clear? Anyone? So let me do that first. So create the temp pointer and edit to point it to head. Okay. Now mention how. So next thing we need to do, we need to shift the head to the next node, head dot next, right? So this is about shifting this head from here to here. Clear? And then you need to delete this guy, right? Delete 10. Delete 10. Okay. Now, when we do this, this node will be deleted. However, we didn't return its value. Someone tell me how do I do that? Amarasinghe DC 3529. So what are the missing steps? How, first tell me, how do I access the value? Amarasinghe, you said, did you say something? Amarasinghe DC 3529.
Yes.
So tell me how do I access the value?
Temp.element.
Okay, good. So let's access the value. Let's name it as return value temp dot element, right? Okay, good. So we have the value now. So we have deleted the node, and then to decrease the size by one, then finally return this value. Is clear? So what we have done here is we have created a temp pointer and pointed it to the head, and then we took out the value of the first node and saved it in this variable return value, and then we shifted the head from here to here, and then we deleted temp, right? So we have deleted this guy, and then we decrement the size, because now when we delete this node, the size will be reduced by one, right? So we need to decrement, decrease the value by one, and then finally return this value. Is clear? Is clear?
Yes.
Okay. So now again, instead of doing all this, let me comment this. So instead of doing all this, we can do it using uh, whatever the functions that is available here. Can someone tell me how to do that? So we need to use the functions available here to implement DQ. Can you take a minute and tell me how to do that? At least in the chat, can you tell me? I had received the answer for the previous question in the chat, but uh, so the method to uh, delete the first node, I believe it's delete first, right? So when you call this, the first node will be deleted, um, right? So however, if you do this, you can't access the value, right? So there are two steps missing. Can someone tell me what are the missing steps? I'll give you 1 minute to figure this out. Yeah, please see how do you implement that, and at least type it in the chat. I prefer if someone can speak out. Okay? I received the correct answer in the chat. No, it's actually not correct. So this delete, you can hear me, right? Am I? Yeah, I'm audible. So this delete first function, if you see, it doesn't return anything, right? So you just delete the node. So there is no return type. So you can't do something like this. It doesn't return anything. So you need to first take out the value of the head. So to do that, what you can simply do is, yep, you can use the head pointer, right? Now we have a pointer called head. You can use that and access the value, right? Then you can delete the first node and then finally return the value. Clear? I think someone got it right from the chat. Is this clear to everyone? Because see, these kind of questions might be coming in the exam, right? I mean, it's not just about exam. So you need to understand the different ways of different ways of implementing these functions. Okay. Um, yeah. Hope it is clear. Okay. So if that was the only thing that I wanted to mention about queue. So we have now implemented queue using both arrays and linked lists. The next data structure we need to do is tree. So we'll be learning about trees now. Let me share the presentation. Okay. So yeah, today we'll be learning about trees. So far we have covered arrays, linked lists, stack, queue, and trees. So this is the last data structure that I'll be teaching. So from after this is done, Mr. Nilmant is going to take over, and then he'll first start with the algorithms, and under the algorithms, the graphs will come in, and also hash tables. From not quite sure whether we're going to do a hash table again. Uh, let's see. Okay, so we so I mentioned that last time data structures can be of physical and logical, right? So now tree is a logical data structure. Now there is another categorization for data structures based on linearity. So some data structures are linear and some are non-linear, right? So arrays, linked list, stack queue, everything that we did so far are linear data structures. Now tree is a non-linear data structure, right? And graph is also non-linear, right? Um, okay. So okay. So a tree data structure, as you can see over here, it comes from the tree. The concept comes from the tree itself. It's actually a upside down tree, right? So now if you rotate this tree by 180 degrees, so here this is the root, right? Here it's the root. So similarly, in the tree data structure, the first node is called the root. The first node is called the root, right? And then we have these branches. Similarly, we have these branches, right? Over here is a branches, and so these are nodes. Let's say these are nodes. Over here are nodes, and finally these are, so similarly these nodes are these guys, and finally over here these last nodes are called leaves. So over here the leaves, right? So the concept comes from the tree shrub. So these are similar to this, root is similar to this, and these are similar to this. So it's like an upside down tree, right? Clear? Okay. Um, Yep. So now a typical tree can be of like this. Sorry for the drawing. So a typical tree can be like this. Uh, yep. So there are a couple of parameters that you need to understand. So first thing is tree is like a hierarchical data structure, right? So there are levels, right? So this is the level 1, this is the level 2. So this is level 1, right? This is level 2. This is level 3, right? So there are levels. So it's a hierarchical data structure. And the first node is called the root, right? The first node is called the root. And, and these are edges, right? So these are edges. And now one thing, so how trees are different from graphs is there are no cycles, right? For example, this is a graph. Now the graph can have cycles. So if you see, there are cycles right over here. These are cycles, whereas in tree there are no cycles. So that's kind of the main difference between a tree and cycle. Sorry, tree and a graph. So this is a graph, right? This is a graph, and this is a tree. So yep, and now uh, these levels. One more thing, these levels are also called depth. Levels and depth goes together, right? Actually, this is level 0. I just messed it up. So this is level 0, this is level 1, this is level 2. I'm sorry for that. So we start with level 0, level 1, level 2. Okay. Yeah, these are the pretty much basic things. Now, as it says, a tree is a nonlinear data structure which can store values in scattered memory location. Now, there is one more thing over here called a binary tree. You may not be able to see, but what you can see it later. So this is a what the word over here is binary. Let me remove the annotation. Yeah, only. So a binary tree can have at most 2 children. The meaning is that, so earlier, if you remember the tree I drew first, it was something like this, right? Here you can see there are 3 branches coming out of this node. In a binary tree, each node will only have 2 branches like this. There can be at most of 2 children. So there won't be more than 2. At most there will be 2, right? So there can be 1 as well, but the maximum is 2. So that's called a, which is called a binary tree, right? So um, so, yeah. So this is example of a binary tree. So this here is the root. You might want to take notes. So these whatever I write here won't be there in the final presentations because I'm actually annotating, right? So you may want to write take notes. Okay. So this is the root node, and then yeah. Now, if you take a single node, it has a value. Obviously, it will have a value. So this 40 is the value and 20 is the value, like that. And apart from that, there will be 3 pointers. Now, if you remember in linked list, there was only single linked list only had 1 pointer, right? Doubly linked list had 2 pointers. Now, this tree has 3 pointers. Now, the pointers are going to so if you take this node, there will be a pointer to a parent. So now a parent is called, like, if you consider this node, its parent is this guy. So one directly up is the parent, right? And now in this example, this node has 2 children, right? So this is one, this is one, right? So these are the 3 links each node has. One goes for the parent, the other 2 goes for the children, right? One left children, one right children. So this is called the left This is called right? So yeah, A is the root node, and the definition is the definition of root node is it's a node without a parent. So if you take this guy, this node, it doesn't have any parents, right? So that's the definition. B and C are children of A. So he's the A, and B and C. These two are A's children, right? So B and C descends from A. And D, E, C are leaf nodes. So D over here, E, C. The nodes at the bottom. So basically, if a node doesn't have any children, that will be a leaf node, right? So it's kind of like in a family hierarchy, right? So the infants in a family are called leaves, right? So similarly, D, E, C are leaf nodes. So these are typical problems we will see in the exams. Like I'll give you a tree and I'll ask you to name what are the root nodes, what are the leaf nodes, etc. So that's kind of a first step. Like in a question, there are a couple of sections, right? So the first part is usually a simple question like this. And D, E are descendants of node A. So over here, D, E are descendants of node A. So DE descends from over here, right? So it's like that. It's like the ancestor, right? So here A is the ancestor of DE, right? The first parent. So right. So DE are descendants of node A, and A is the ancestor of DE. Yeah. Okay. Advantages. So a couple of advantages. Again, the first thing, size is not fixed, right? That's one of the main advantages. Size is not fixed. You can have any as much as nodes you want. When you add nodes, the tree will grow, right? So it will starting from root, it will go down. So searching is faster than linked list. Okay. Can someone tell me how this is possible? Okay, before going into this, actually, this is an advantage of binary search tree that we will learn in the next slide. I'll explain how this advantage comes about there. So the disadvantages are doesn't have direct access to element even if the value is known, right? That means if you know even the value, you can't directly access this one. So if you know that you want to access this, there's a node with value 25. If you want to access this guy, you can't directly access it, right? So you have to start from the root and comes all the way up over here to access this guy, right? Now, in even in linked list, it's so you have this head and tail, right? So you don't have to go from, especially in doubly linked list, you don't have to go from all the way from the head node, right? So whereas in this example in tree, you will have to go from root, start from root and go all the way up or down over here to access this node. Okay. And one of the main disadvantages, this deletion operation is quite complex. So you will learn why is that later. So these are the advantages and disadvantages. Okay. Now we go to a special kind of tree called a binary search tree. Clear the annotation. Okay. Binary search tree. So now the difference between a binary tree and a binary search tree, a binary search tree, we call it BST, is an ordered binary tree with the following properties. So the important word is ordered. Is this tree is in a particular order, right? So what's the order? Let's see. The left subtree of a node contains only nodes with keys lesser than nodes key. So what this mean is a key is the value. So simply the value is called the key, right? Right. Now what this sentence means is the left subtree. For example, let's take the root. The left subtree is of root is this guy. All these together is a subtree, right? A subtree of the main tree, right? So now whatever the nodes that we have on the left side from this node will have a lesser value than this value. So root's value is 40, right? Just forget that this is the root. Just say that this is a normal node. So its value is, or the key is 40. Now all the nodes that are in the left subtree of this node, right, I'll have values lower than that. Clear? It's 40 and this is 20, 10, 25. So all are less than 40. Right? Similarly, the right subtree of a node contains only node with keys greater than the node's key. So similarly, the right subtree, the values will be higher than this node. Right? This 100 is higher than 40. This is applicable or is valid for all the nodes. Now, if we take this node, now nodes to the left, that means this guy is lower than 20, right? And nodes to the right, that means this guy is higher than 20, that's 25. Clear? The left and right subtree each must also be a binary search tree. So that means, like, again, the same thing that I mentioned. So from here, this subtree itself should be of the same order, right? Right? So I mean, so if we when we go to this subtree, this two, if we consider this node, the nodes to the left should be of lower value and nodes to the right should be of higher value, right? So that's the meaning of the third sentence. And there must be no duplicate nodes. So there shouldn't be any nodes with the same value. Is this clear? This is important for you to understand, the because we won't be discussing about binary trees anymore. So we will be focusing on binary search tree from here onward. So this order you need to understand clearly. Yeah, one advantage of this binary search tree is the insert, delete, and traverse operations are much efficient in a binary search tree than in a binary tree. I hope it's quite clear, right? Because now the nodes are in a particular order, right? So because of that, insertion, deletion, search especially is quite efficient than in a binary tree. Because in a binary tree, the nodes are in not a particular order, right? So in the binary tree, the first node can be 40, and maybe this one can be 25, this one maybe 100, like this. So there's no order. So this one may be 10. There's no order, right? So it's very hard to insert or delete in a binary tree. Whereas in a binary search tree, there is an order so that we can use for different operations. Now, can someone tell me why in binary search tree? Now, if you go to one slide back, right here, I mentioned searching is faster than linked list in binary search tree. Can you tell me why is that? Anyone? Take a minute and try to figure it out why the search operation is faster. Anyone? Uh, Jayakodi 3609. Can you tell me why the search operation is faster in binary search tree?
Because unlike the normal binary, it has a certain order.
Yeah,
That's
wow.
reason.
Yeah, why is it faster than linked list then? I mean, the question is actually why binary search tree is faster than linked list. The answer is actually the order, but can you explain maybe with example or with more details, like why is it faster than linked list?
I have no idea about that.
Okay, so the reason is we take another color. Okay, the reason is now there's a particular order, right? So all the nodes into on the left hand side is has a lower value, and all the nodes in the right hand side has a higher value. Like that, there's a particular order. So now when you start to search from the top, right? Okay, so when you start to search from the top, I mean from here, now say you are searching the value 25, right? So when you start from here, you only need to go in this way, right? Because now value over here is 40, right? Value over here is 40. Now we know 25 is lower than that. So we know that node should be on this subtree, right? So you can just forget about whatever the nodes that is over there. So let's say there are many nodes over here. So you don't need to search any of these nodes because we know the value is over here on this side, right? So basically take out half. Let's say this is a symmetric tree. If this is a symmetric tree, we basically take out half of the node in the first, at the beginning itself, right? Then we go to over here. This is the value is for 20 and we are looking for 25. Then we know that that node should be in a subtree over here. Let's say there are more nodes over here. That the 25 should be over here. So we basically take out all the subtrees, all the nodes over here, right? Similarly, when you go deeper and deeper, the number of nodes that you need to search, right, is getting lower and lower. So that's why the search operation is quite fast in binary search tree, right? Whereas in the linked list, it's no, right? I mean, you'll have to go from the first node and all the way one by one until you find the required node, right? So that's the difference about that's actually the one of the main advantages of binary search tree. Okay, that's why actually the name itself is binary search tree. See, I mean, unlike in any other data structures, the search, the value, the word search is there in the name itself. So yeah, that's the main advantage. Okay. Okay then. So now with this, maybe I'll do example and let's go to the next slide. Okay. Let me do example. Is there like a whiteboard I can share? Yeah. Can you see the whiteboard? Can you? Hello? Anyone?
No, sir.
No. Can you see it now? The whiteboard.
Yes, sir.
Right? Okay. So let's do example. Don't have the drawing pad, so okay, let's say you have a list of numbers 100, 55, 60, 120, 40, 115, 50, 75, and 130. Okay, so you are given a set of numbers and you need to insert these numbers into a binary search tree. So that's the question, right? So these numbers you have to insert from as it comes. So we start with 100. So 100 will be the root node, right? So 100, and then 55. 55 is lower than 100, so needs to go to which side? Where should we put 55?
the left side.
Yeah, correct. So it goes over here, 55, and then 60. 60 is, okay, we start with root. 60 is lower than 100. So here comes over here. And 60 is higher than 55, right? So it goes over here, 60. Then 120. 120 is higher than 100. So it goes over here. And then 40. 40 is lower than 100, lower than 55. It goes over here. And then 115. So higher than 100 comes over here, lower than 120, right? So it goes to over here. Sorry for the bad drawing. So I hope it's clear. So there are levels. So this is one level, level 0, level 2, and all these are in level C, level 0, 1, 2. Okay. 15, then 150. 150 higher than 100, higher than 120. So it comes over here. 150. 75 lower than 100, right? Comes over here. Higher than 55 comes over here. Higher than 60, that means it goes over here. So one thing actually you need to make sure when you start writing, when you start drawing a tree, now make sure you span these two branches as much as possible. Like instead of writing like this, draw it like this, so that when there are more nodes adding up, so you won't face a situation like this, right? So here what because I didn't stretch it all the way up to over here, so now 75 actually goes below 115, whereas it belongs to this subtree. Right? Just a hint when you write the trees, it will be easier for you, especially in the papers. You don't have to rewrite the whole answer again. Okay, 75 and then 130. 130 from here over here, higher than 120, comes over here, lower than 150. That means should be over here. Clear? Okay. I'll give you one more example. Just take a minute to note this down, then I'll give you example for you to work yourself. Yeah. Can I delete this? Anyone still writing? Please raise your hands if you are still writing. Okay, anyway, I'll just write it here. So example 2. Okay, example 2, write these down. The first value is 80, the second value is 70, 60, 95, 67, 120, 105, 50, 100. Okay, can you work this out by yourself? Try to draw the corresponding binary search tree. Please ask if you have any questions. Let's work this out. So we start with 80, right? So the root node is 80. And then we have 70, right? 70 is lower than 80. So it goes over here. And then 60. 60 is again lower than 80, lower than 70. It goes over here. And then 95. 95 is higher than 80. So it goes over here. Then 67. So it's lower than 80, lower than 70, higher than 60. So it goes over here. 67, then 120 goes over here. Then 105, higher than 95, lower than 120. So it goes over here, right? 105, 50. It comes all the way over here. So 50. Then finally 100. 100, larger than 95, lower than 120, lower than 105. 100 is over here. Now, I hope you got it right. This is very important. Why is now a typical question in the exam paper may look like this. So I might give you a set of numbers and I might ask you to draw the binary search tree. And then I might ask you to if or say what is the root node, what are the leaf nodes, what are the what's the height of the tree. Like that I might ask you questions from the tree that you drew, right? So now if you get this wrong, if you get this tree wrong, all of your answers from there will be wrong, right? So a significant portion of the marks will be deducted in that case, right? So make sure you get this right, the concept right. Okay. Yeah, one more thing. I'm not sure whether I inform you this at the beginning of the module. Now, in the MIS, there is a clause that says you need to attempt all the continuous assessments to pass the module. I mean, it's not about just scoring 35% from the continuous mark, but you will have to also attend all the continuous assessment. For example, if you don't submit the assignment that I give you, right, you won't be able to sit for the final exam. Basically, you will fail the module. At least you will have to submit a blank paper, right? So, I mean, you need to attempt each assignment, each continuous assessment component in order to pass the module. So make sure you do that, because we had a situation in the I think the last time there was the student who had scored more than 35% from the continuous assessment, but he has failed to submit one assignment. So because of that, he failed the module, right? So make sure that doesn't happen to you. Okay, at least submit a blank sheet if you don't know the answer, right? At least submit a blank sheet. Okay. Okay, hope you got this right. Any questions from this tree? Any questions from the basically the concept of binary search tree? No. Okay. Okay, then let's do some coding now. Okay, so okay, so in order to implement the binary search tree first, we need to implement the node class, right? So I mentioned here we have three links, right? So one link goes to the parent, one link goes to the left child, and one link goes to the right child, right? So we have a key is basically the value, and the link to left child, right child, and the parent, right? So with the default constructor, you can just specify maybe key as -1, and all this will be null. And if you have a constructor with the value self, so the value will be assigned to key, and all this will be null, right? Okay, let's do a coding example. Hope you can see the Visual Studio screen. Can you see the Visual Studio screen?
Yes, sir.
Okay. Now let's delete all this. So yeah, let's start with the node class. Okay, do we need define them publicly? So we need a key, we need a node to parent, a node to left child, a node to right child, right? Okay, then we need a constructor. Key is assign -1 because we are not passing any. Okay, left. This is the overloaded constructor. So this is the node class. Just give you a minute to write this down. So about your arrival to the faculty. So hope you are all are aware, right? So you'll need to come to the faculty on 24th, right?
Yes, sir.
Okay. So yeah, one more thing. This Friday's lecture we won't be able to do because there is a research presentation evaluation all day. I think all the classes will be cancelled. So I think all the lectures will be there. So lecturers will be there. So we can't do Friday classes. So with that, I think we are missing. Last time also we missed. How many hours did we miss, Saranga?
2 hours.
2 hours. I mean, with this Friday class, is it?
Yes, sir.
Okay. So before I hand it over to Mr. Nilmantha, let's schedule one more class so that I can. My plan was to the complete free and then do a tutorial session using, I mean, based on all the data structures, then hand it over to Mr. Nilmantha. So let's let's see how it goes. Yeah. Okay. Hope this is clear and you have written this down. Next thing we need to create a binary search tree class. I'll just write it as BST. Okay, binary search tree in short form BST. So we need to have a root node and then size. These are the only two variables that we're gonna be needing. The constructor needs to be there. Root will be null at the beginning and size will be 0. Any questions? Please raise hands if you have any questions. So basically this to write root and the size we need to have. And then the next thing is insert operation. Okay, so now we have the node class ready, right? Node class ready. The binary search tree class, the parameters are there. So now we need to implement the functions. The first function, so obviously will be the insert function, right? So this is the signature. So if you don't know what is a signature, signature is basically the definition of the function. So this is a signature. If I ask you to write the signature of a function, this you should write this one. Okay, this is a definition of a function or the signature. Okay. So let's start. Let's create a node. Create the node. Node star temp. We have created a node. Sorry, a new. Right. So we have created a node with this key now, and the pointer name is temp. Now this insert operation. I'm sure you understand this now, right? So in order to insert a node, I explained this using two examples. So we need to have this order, right? So the right. So for example, so this is the root node. Let's say this is our tree now. Now the new node that will be coming up. So the node that we need to insert, we need to find out the place that this node needs to be inserted, right? Based on the current status of the tree, right? So it can be this one, it can be this one, so we can this one. So basically we need to find out to where we need to insert, right? So in order to do that, we need to traverse through this tree and find out the place, right? So in order to traverse, the meaning of traverse is search and go through the tree, right? Okay. So we gonna be needing two more. We can be done with one pointer as well, but just to make it easier, I'm going to use two pointers. One is current, the other one is, let's say, previous. So these two pointers will be used in finding out the place of the insertion. So we start current with root. That means I'll explain maybe two examples. Let's say this is 40. So this is 20. I think I had example in the presentation. Yeah, insert. Yeah, there's example over here. So let's take this example. Okay. So here in this example, we are inserting a node with key 5, right? The value 5. Okay. So this is the current tree. So in order to insert 5, so we need to find out the place, and this place will be, so 5 is lower than 40. You need to go here. So 20 is lower, 5 is lower than 20. You need to go to the left side. 5 is lower than 10. That means you need to insert it over here, right? Okay, so now we start with the current pointer, right? So we start the current pointer, we pointing to root, right? Current, right? And then previous pointer, it will be null. So that's how we start. Let me go over to here. Okay. The first thing, the thing we need to do now is basically we need to iterate the current pointer until it goes null. So we start with the root, right? We start with the root, and we'll be basically going down from the root to find out the place. So if now we know the value of the node, right? If the key that we're going to insert is lower than current dot key, so then that means to which side do we want to go? So this is clear. So what we are doing over here is we are checking the key, right? In this example, 5, right? 5, whether it is lower than 40, right? So if it is lower than 40, to which side do we need to go? Anyone? Fernando, 3585.
Left side, sir.
Okay. Yeah. So we need to move our current pointer to left side, right? So we'll just write current equal current dot left. So we are moving to left side now. Else, okay, else if key is higher than current dot key, that means we need to go to right side, right? We are shifting our key to right side. Okay, clear? Else, if now there can be a situation where the key is equal. For example, the key that the user is asking us to insert might be 40. So that means a duplicate, right? If it is a duplicate key, we can't insert, right? Remember, binary search tree don't have any duplicate keys. So we have to inform that to the user, right? And then they return the function from here. Stop the function from here. Okay, clear? Okay. So when this while loop is executed, we will basically the current pointer will go so the current pointer we started from here, right? So we started from here. Now current the key is 5 is lower than 40, then current pointer we shifted to over here to the left side. 20 the 5 is lower than 20, so we shift to again left side, we move to left side. And now 5 is again lower than 10, so we move to left side. So the current pointer will actually end up in this null. So if there is no node, it will be null, right? So current pointer will end up over here. In order to, because now we need access to this node, right? In order to add the node, we need access to this node, so that we defined another pointer called previous here, right? We defined another pointer called previous. Now the previous pointer needs to be one step behind. So the thing that was missing is here we need to make sure when the current pointer is shifting, we need to make sure one step behind the current pointer, the previous pointer needs to be there, right? So we need to assign whatever the status of current pointer to previous pointer, right? Before we shift the current pointer, right? We do the shifting over here, right? So before do the shifting or before we move the current pointer, whatever its previous value, we have assigned it to the previous pointer. Clear? Okay, so let's do that over here. So previous needs to be equal to current. Okay. Okay. So when this while loop is executed, that means at the end, what we'll have is, okay, what we'll have is the previous pointer will be over here. Previous pointer will be over here. Current pointer will be null over here. Okay. So so we'll be using this one to insert the node now. Okay. Maybe I'll explain over here and go to the code. So now when this while loop, so this is the while loop, once it is executed, we'll have the previous pointer pointing to the parent, right? So basically it will be pointing to the parent of the new node that we're going to insert, right? So we'll just check a couple of things we need to check. If previous is exactly equal to null, that means this never happened, right? That means the tree is empty. I mean, if it is null, that means this while loop never executed. So previous was null. So if it is null, it will just assign the root, the temp as root, right? So now the new node will be the root. So there's only one node now, and no children, nothing, just one node. Else, now remember previous ended up over here, right? Previous pointer ended up over here. Now we need to again make sure the side, like the 5 is whether it should be inserted into the left side or to the right side, because this node has two links, right? One left, one right. For example, if the value of this new node is let's say 12, it needs to go over to here. Now it is because 5, it's because it's 5, it will be inserted onto the left side. So that one we need to check. How do we check? The key, we compare it with the value of the previous node. Sorry. So if the key is higher, that means the insertion will be on the right side, right? We insert into the right side. If the key is lower, we insert into the left side, right? So yeah, that's the step. Please let me know if I am missing anything or I'm doing it wrong. Okay. Okay. So the while loop ends over here, right? First thing we need to check if the previous is exactly equal to null. That means there were no nodes in the tree. The root will be temp. Yeah, root will be temp. Okay. Else, if you check whether the key is lower than the previous node's key, that means the insertion happened in which side? If the key is lower, anybody? Attanayaka 3537.
In the left side, sir.
Yeah. So basically we are in a position now. Previous is over here. That he doesn't have any children, right? So we need to figure out whether the temp will be over here, right? So we have created a temp. So we need to figure out whether, I mean, this parent has 3 links, right? So we need to figure out whether we are going to connect this link to here or this link to here, right? Okay. So if the key is lower, that means we are going into the left side, right? So, so if it is the left side, how the insertion happens? Okay, can someone tell me that there are 2 steps here? What are the 2 steps? Kumar Singh 3645. How do we insert this node to the left side? We'll have to use previous, right? The previous is
Previous dot left
left, yeah.
equal temp.
Yeah, good. Next thing,
Increase the size.
yeah, that's also there. Let's increase the size at the end. One more thing. Yeah, okay, I thought, yeah. So if you remember now, each node has three links, right? So even the temp has three links, one to the left, one to the right, one to the parent. We need to connect the parent as well. So we connected only the child. So the child link, right? This node's child link, we connected to over here to here. Now we need to connect this node's parent link to this node, right? Oh, is that clear?
Yes, sir.
Okay. So temp dot
Parent.
parent, yeah, parent should be previous. Clear? Okay, temp dot parent should be previous. Okay, and then now else if the key is higher than the previous key, then we need to insert it to the right side. So previous dot right is temp. Temp's parent should be previous. And then what else we need to do? Yeah, increase the size by 1. Think, yeah, I think I covered everything. Yeah, okay. Is clear? I'll give you maybe 1 minute or 2 minutes for you to write this down. Any questions? Please ask or type it in the chat. There's one more announcement, like so those who received hostel okay, I'll explain again. So here we are implementing a search operation. So we'll basically search whether a given key exists in the tree or not, and we'll output whether if it exists, we'll output true. If it doesn't, we'll output false. So that's the return type is a Boolean type. First thing we need to check whether the tree is empty. Can do that by checking whether root is equal to null. So if it is null, we just output tree is empty. Else, that means there's a tree with a couple of nodes. So we need to search, right? So we just need a 1 pointer in this case because we are not going to do insertion. So we are just searching, right? So 1 pointer is enough, and we start from the root, and we'll go all the way until current is equal to null. And in each step, what we are going to do is we're going to check whether the current key is equal to the given key. If it is equal, that means there's a match, right? Then we have found the node. So what do we need to output here? Anyone? Come on, anyone? What do we need to output? Appu. What's your registration number? It was here. Okay, Bandar, can you tell me the answer? Saranga. What do we need to output here?
Return one.
One. So if you see here, it's a Boolean type, right? The return type is Boolean. We need to either output true or false. So one actually sometimes goes as a synonym for true, but the correct thing is true. So we need to output true, say that, and we found the key, right? Else, same thing we need to do. Else, we need to go down and see. We need to basically shift the current pointer. We check whether the current pointer's keys. Let's just whether key is lower than the current key, current pointer's key. So that means if the key is lower, to which side do we need to go? Anyone? I need to stop at 2:15 today because there is a faculty board in at 2:30. Can someone tell me to which side do we need to go if the key is lower than the current key? So basically what we are doing is, so we have a tree like this, right? So we start the current pointer from the root and then we go down, right? So let's say our current pointer is over here now. Now we know the key, right? So we know the current pointer's key, that means the key over here, we know that as well. So basically now compare this with here, right? So if the given key is lower, that means we are going to the left side, right? If the given key is lower than this key, we are going to the left side. Clear? Okay, so we go to the left side. Else if the key is higher, we go to the right side. Clear? This clear? Okay. Okay, so once we have this loop executed, that, and if it doesn't comes over here, that means we haven't found a key, node with the given key, right? So if it goes all the way until null, that means the current pointer start from here, goes here, and then null. That means there is no node with a given key, right? So we can simply mention that search key is not found or doesn't exist, whatever. Okay. And then we can simply over here return false. I mean, if it comes over to here, that means the key is not found, right? If the key is found, it will somehow comes to here. This inside this function, it will go over here. So if it doesn't go here, and if it comes over here to the end of the function, that means the key is not found. So we will return false. Okay. Okay. So let's create a tree. So we just created the function. So we need to now call this functions, right? We need to create a tree and call these functions, right? So let's add a couple of nodes. Insert 59. 20. Um, 9, 6. Like this. So we have created a tree with 5 nodes now. The unfortunate thing about trees, it's not quite easy to graphically print this tree, right? Because it's a hierarchical type. Unlike in linked list and everything, the print function is not quite simple. So I'm not going to explain the print function. I want you to try it yourself and try to see whether you can draw a tree, right? Based on the current status of the tree, see whether you can print the tree as in a tree. I mean, not as in a linear type, as in a like this over here. Try to see whether you can print it. Let's try our search method. Let's see whether it works or not. So let's search something that is there in the tree. Maybe 59. Let's search that. And let's also search a value that is not there. The 100. Let's run this and see what are the outputs. So the first one, the key is key exists. So we found the key. And second one, 100 wasn't there, right? 100 is not one of the nodes. So key is not found, right? So that means our search function works. So the homework today will be, so we'll stop from here today because of the faculty board. The homework for you today is try to implement the search or the, sorry, not the search, print function for the tree data structure, right? So ideally, if you can, it will be very hard, but the code is there on the internet, but try to do it yourself. So if you can print it like this, that would be very good. So if you can print a tree like this on the console, that would be very good. There are other ways to print a tree, like in a descending way, like this, and maybe from here, like this. There are other ways to print. That's also fine, but if you can do this, that will be very good. And this is also fine. And please try to do that, and I'll use one of your codes in the next lecture to print. Okay. Yeah, if you can do this, maybe please send that code to me via email. Okay. I'll be using one of those codes in the next lecture. Okay. So I think that's it for today. Any questions? We have a couple of minutes.